Hello everybody, in this video I'm going to explain the parabola just like I had promised in my first video. Um, we'll go into the details concerning the parabola and the general formula of a parabola, then we'll move on to determining the coordinates of the focus and the directrix, the tangency, how to find the equation of the tangent for a parabola, and some characteristics that are related to the parabola and only to the parabola, not to any other conic. So first of all, the general formula of the parabola. We have four styles of parabolas. In the first video, in the introduction to conics, I had shown you one of the four styles of the parabola. Unlike the hyperbola or the ellipse, which each have two different styles, for the parabola it's four different styles. In a minute I'm going to show you clear images of the four styles. For now, I'd like you to focus on the vertex of the parabola. In our introductory video, we had taken the vertex of the parabola as 0, 0 for the purpose of simplification, but it's not always the case. The vertex of the parabola doesn't have to be the point O of coordinates 0, 0. It might be any other point. It might be point of coordinates, point A of coordinates 1, 2, point B of coordinates 3, 4. So whenever we change the coordinates of the parabola, the general formula of a parabola might change. As you can see here, if S were to be the vertex of the parabola, S would have coordinates x of S and y of S, obviously. So um, going back to the style of the parabola that we had seen before, in which we'll show you again in a couple of minutes, the equation of the parabola would now look like this. Y minus y of S to the power 2 would be equal to 2p into x minus x of S. So why did we say that there are four styles? Because, again, in this case, for the simplification purposes, I'll take O as the center, as the vertex of the parabola. We have these four equations. All these four equations here represent equations of a parabola. We could say that y squared equal to px. We could say that y squared equal minus 2px, or that x squared equal to py, or that x squared equal minus 2py. In our introductory video, we had taken 2p as 8. Now, why exactly did I say 2p? Why not constant a or constant b? Why exactly 2p? Because through this constant, we can determine the coordinate of the focus, the coordinates of the focus and the coordinates of the directrix, which is why we call it 2p and not just any constant a. So I'll show you all four types, all four styles of a parabola. So in this case, y squared equal 8x. This is the equation of, this is the shape of the parabola in the graph when y squared is equal to 8x. As you can see here, that parabola is of vertex 0, because the general formula, the actual general formula would be y minus y of center to the power 2 would be equal to 2p, in this case 2p being equal to 8, into x minus x of center, in this case the x of the center being 0. So when we simplify that, we get y squared equal 8x. This is one of four styles of a parabola. This is y squared equal 8x. In this case, the squaring is given or dedicated to the ordinate y. Now, what if I had given x a negative coefficient? What if the coefficient of x was minus 2p? What if the equation was y minus y of center, all of it to the power 2, equal to minus 2p into x minus x of the center. In this case, again, we're taking the center as 0 for simplification purposes, as O of coordinates 0, 0. So I'll focus on this now. Y squared equal minus 8x. This would be the equation. This would be the graph of the parabola, as you can see here. So in the first example, y squared equal 8x, we see that the parabola shifts towards the positive sense of the abscissa. And the abscissa would be a center of symmetry in this case, being in this case, only in this case, we see that the abscissa is a center of symmetry. So whenever x has a positive coefficient, we'll see that the parabola shifts towards the right. Whenever we give x a negative coefficient, the parabola will shift towards the left, towards minus infinity, when in accordance to the x-axis. Now, what if we had squared x and given y the coefficient 2p? This would be the shape of the parabola. Now again, we see that it moves upward, it opens upward, it's got a U shape definitely, but it opens upwards because the coefficient of y is positive. So you might conclude that if x squared was equal to to y being multiplied by a negative coefficient, would give us a parabola shifting towards the negative value of y-axis. And that is exactly true. So for the purple violet colored graph that we see here, y is given a negative coefficient. So we give y a negative coefficient and we see that the parabola moves towards minus infinity with respect to y-axis, So we had talked about the general formula being y minus y of the center to the power squared, to the power 2, as you can see here, being equal to 2p, in this case being 8, into x minus x of center. So if I gave you guys this equation, you would conclude that the center of the parabola in this case would be 1, 2. So x of the center s is 1 and y of the center s is 2. 2p would be equal to 8. So let us draw this. As you can see, the vertex of that parabola is somewhere over here, but it's definitely not point O. I'll keep point O, I won't delete point O for the purpose of reference, so you can look at it and see what I mean. Actually, point S is the vertex of the parabola in this case. And point S is of coordinates 1, 2, which is exactly compatible with what we had said a moment earlier, that following the general formula of a parabola, this would be the vertex of the parabola. It would have coordinates 1 and 2. Now, what about the focus of the parabola? I'll draw the focus and I'll draw the directrix of the parabola, and then I'll insert this graph so we can study it clearly. I'll enlarge this just like we used to do, and then we'll discuss this. So this is our graph here. This is the focus, and this is point S, and this is the parabola. The black curve represents the parabola, the green line represents the directrix, and point F definitely represents the focus. So why exactly did I tell you that we cannot simply say that y squared in this case is equal to constant times x? We said that we refer to that constant as 2p. Now, it doesn't have to be p, it could be 2 z, 2w, but let us take it as 2p. We cannot refer to 2p as any other constant, a or b or c, for this purpose, because 2p in this case was 8. In the case of this parabola, it was 8, which means that p would be 8 divided by 2, which means that p is equal to 4, and p over 2 would be equal to 4 over 2, which means that p over 2 is equal to 2. Now, why are we saying all of this? Why did we get into so many details? Because that is the way that we can actually find the focus of a parabola of a vertex different than point O of coordinates 0, 0. So the focus will always have, the coordinates of the focus will always follow this general formula. P over 2 plus x of the center and y of the center. That is considering that the parabola is of general formula y square of general formula y of this general formula that you see over here. I'm moving the cursor over that general formula. So if the general formula was the other way around, if we had said that x minus x of s to the power 2 would be equal to 2p into y minus y of s, we would have shifted these two coordinates over here. So it would be p over 2, it would be x of s and p over 2 plus y of s, not p over 2 plus x of s, y of s. Now we found out how to find the focus. Focusing on the example I had given, um, and focusing on the general formula, we see that after finding p over 2 and after making sure that we've got the right style of parabola, that we know what style of parabola out of these four are we working with, are we dealing with, it would become pretty easy to find the focus. So I'll give you a case-by-case study. If this were the general formula of the parabola, the focus would have the following coordinates: p over 2 plus x of the center and y of the center. Now, if 2p were negative, were a negative constant, it would complicate things a little because we wouldn't be able to insert p over 2 plus x of s, as in this case being the center or the vertex, as we wouldn't be able to insert p over 2 plus x of s as the abscissa of the focus. Instead, it would be minus p over 2 plus x of s. So p over 2 follows the sign of 2p, which is why, again, we denote the constant as 2p. So what if the general formula was, what if we had squared x and not y? It would turn things around. I have already explained this. The focus. What if, let us take this example. We squared x rather than y, and the coefficient 2p was positive. The coordinates of the focus of the parabola would be x of s and p over 2 plus y of s. So after memorizing one general formula and the respective formula for finding out the coordinates of the focus, it would be pretty easy to figure out the rest, which is why I didn't bother writing them down anyway. We have got no space. For the directrix, we remember that from our introductory video, you must remember that the directrix is symmetric to the focus with respect to the vertex, which means that in this case of this graph, the directrix would have the following coordinates: minus p over 2 plus x of s and y of s. Actually, I've written it down, but okay, I must figure out a way to minimize the explanation through each video. Until then, I hope it's clear for you guys. Now, moving on to the tangency. Moving on to the tangency of the parabola. The general formula of a tangent of a parabola, and that is a tangent at a point E, as I had given in this example, would be y minus y of E would be equal to slope into x minus x of E. When we say y prime, it's basically the slope. When we talk about functions, f prime of x would be the slope. So it's the same case over here. A positive slope would mean that there's a positive inclination, that the line is moving upwards, and the negative slope would mean that the line is moving downwards, that we have a negative inclination. So to get the slope of a parabola, we need to derive the equation of the parabola. Otherwise, there's no way to actually find out what y prime is. In this case, it's y prime. Then again, if we had taken x squared, it would be the other way around. So for finding the slope, we derive the equation of the parabola. Let us take the usual equation that we're taking, the simple equation of y squared equal to 8x. The derivative, we know that in mathematics the variable is x, in physics the variable is t, so x prime would be definitely equal to 1, and in physics t prime would be definitely equal to 1. That is not the case with y. Y is not the variable. We are not deriving by y, we're deriving by x, which is why y is y prime. The derivative of y is y prime, but it's not 1, unless y were the variable. So how exactly do we derive a number or a value that is not the variable? This way. We've got y squared. Let us derive y squared. So we move to the coefficient. 2 becomes a coefficient. We multiply it by y to the power 2 minus 1 times y prime. We'll make another video explaining derivation in details. So for y squared, it's 2y prime equal 8. Again, 8x, the derivative of 8x would be 8 because x as a deriving x would render it 1. So 2y prime is equal to x, which means that y prime is equal to 8 over 2y. Now, in the case of the tangency at point E of coordinates 2, 4, mind you, point E belongs to the parabola, otherwise there is no way that we can find a tangent. A tangent means that it intersects the conic or the curve at one point. So E definitely belongs to the parabola and it's got coordinates 2, 4. Y prime is equal to 8 over 2y. How do we find the slope of the tangent at this point? Simply substitute the coordinates with the coordinates of the point of tangency. So 8 over 2y would be equal to 8 over 2 times 4, which means it's equal to 8 over 8, which means that y prime in this case, the slope is equal to 1. Now back to the general formula, y minus y of e is equal to y prime of e into x minus x of e. We'll see that the equation of the slope would become y minus 4 equal to 1 into x minus 2. Expanding and moving the constants to one side, the final equation of the tangent would be equal to y equal x plus 2. I'll show you that in a minute. So here's what we'll do. We'll draw this graph in which point E is tangent, so you can see what I mean, plus there's a small note that I'm going to give you guys, so we need this graph in front of us. I'll insert the graph, typical like we usually do, insert the graph, we enlarge it, we discuss it. X equals to minus 2, that is the directrix, and this is the focus. I'll keep point O for reference, it's got nothing to do here, but I'll keep it for the sake of reference. And this is the graph. Now let us expand this and discuss this. I'll have to draw. In this case, we see that point T actually does belong to the graph. We had said that point E has got coordinates 2 and 4. So let us just substitute that in the equation y squared equal to px. So instead of x equal to px, in this case, let us substitute it in the following equation, y squared equal 8x. We had said that E has got coordinates 2, 4. So 8 times 2 is equal to 16, and 4 squared is also equal to 16, which means that E does in fact belong to the parabola. As we can see, it does belong to the parabola. Point F is the focus. We had already discussed how to find the focus anyway. In this case, we've got the vertex at the point O. And then again, we've got H. H in this case is the orthogonal projection of E on H. Now, I'll get back to that in a minute. Let us focus right now on the tangent. The equation of the tangent is y equal x plus 2. Now, how do I make sure that I've got the right equation of the tangent? I can simply substitute with the coordinates of E like I've been doing all along. Y equal x plus 2. The coordinates of E are, once more, I repeat, 2, 4. So 2 plus 2 is equal to 4, and y is also equal to 4, which means that E is compatible with this equation. It does belong to this equation, which means that E does belong to this line. And we had already gone through all the steps to make sure that the equation of the line we're getting is the equation of the slope. Now, there is a small detail that we've got to know when it comes to the parabola. This has only got to do with the parabola. It's got nothing to do with the ellipse. It's got nothing to do with a hyperbola. It's a characteristic related to the parabola only and only to the parabola. What if I were to draw a line from E to the focus? Remember that the eccentricity is equal to 1. In parabola, we had already discussed that in the introductory video. I don't want to lose any more time repeating what I had already said, so let's get back to this. In this case, we can see that EF again is equal to EH, which means that triangle HEF is an isosceles triangle of vertex E. Now, the tangent of the parabola at a point E is also the bisector of the angle HEF. Since HEF is an isosceles triangle, considering that the length of EF is equal to the distance from E to H, which means it's equal to EH. So I'll repeat again, the tangent of the parabola at a certain point E is also the bisector of the angle HEF. Now, how do we find that angle? We find it again by drawing the orthogonal projection of E towards the directrix and by joining the point with the focus. That was all for this video. Thank you for watching. If you've got any questions, leave them in the comments section and I'll be pleased to answer all your questions. And until we meet again, thank you.